So welcome everybody again, and this is the continuation of our exercise sheet number 3.1, which we started last week by solving this interesting system of linear equations on a field with only 3 elements. So this was a little bit exotic in a way, but from now on we will generally allow for real numbers, so there's no restriction anymore. And exercise 3.1 number 2, if I may say, is meant to make clear questions of solvability, in the sense that you may have a system of linear equations, short SLE, which is not uniquely solvable. So there is not one unique solution. There may be a sort of a under how do you say in English? It may turn out that the whole system is underdetermined. That's what I wanted to say. So that a whole infinity, in this case, of solutions appears. If you compare with our solution of the previous exercise, you remember that we had this case by the appearance of a, as I said, a clean zero row, which had the consequence that we were forced to introduce a free solution parameter. But in this special case, this led to only 3 different actual solutions, due to the fact that the field on which the whole system was declared contains only 3 elements. If we now switch to real numbers as a as a basic set, this case would have turned immediately into a so-called solution line, which is really a linear collection of all the solutions which you could even geometrically display in this case, a 4-dimensional representation of the whole system, which is graphically possibly not so easy, but it's also possible to make some projection. But also algebraically, you can say that such solutions which are not unique may always be represented graphically as linear objects in a graphical representation of the vector space, which they may be lines, they may be whole planes, or even subspaces of a higher dimensional vector space. So that's an interesting topic by itself, to make all these solutions or all these systems of linear equations visually alive. So sort of making them visible. Okay, so it might happen this time that we get a whole line, an infinite line of possible solutions. We'll wait and see. And the other possibility, of course, is that such a system is not even solvable, so that there is not even a single solution. But it's important, perhaps already at this moment, to understand that in order to make such a system unsolvable, it's necessary that it's structurally underdetermined or overdetermined. Even this is possible, but what I mean is, if I get a zero row which contains a contradiction in the end, this makes the whole system corrupt, so that it is not solvable. It hasn't even a single solution anymore. So that's closely connected, the 2 cases of underdetermined SLEs with an infinity of solutions, and on the other hand, systems which have not even a single solution. These 2 cases have to be separated from the other case in which a unique solution exists. this has very much to do with the so-called determinant of the according determinant of the coefficient matrix. So since I'm not sure whether you talked about determinants in the lecture, I will put this delay this for a while. But if you're able to calculate the determinant of a, for example, a 3x3 matrix, it's a big advantage because you can decide beforehand whether a unique solution exists or whether it doesn't. We will not do this. We will start right now, right away, solving this first example by a standard method called Gauss-Jordan elimination, which I have already used last time. And I know that Martin did not really handle this in the lecture, but it's just a little extension to the well-known Gaussian elimination methods. I start and explain on by doing, learning by doing. That's what that's what we do. Okay, so my short notation again is coefficient matrix pipe vector B. You remember what this means. This is the short notation for a whole system of linear equations where every row represents one of the equations left side, and every number of this vector represents the right side of one of these equations. So the first line, for example, would read x1 minus 3 times x2 plus 5 times x3 equals 26, and so it goes on. So what's the procedure? The procedure always runs from the upper, well, you could say the upper left corner until or up to the lower right corner of the coefficient matrix, not regarding the extension by these numbers, which are, well, responsible for adjusting the solution. If a unique solution exists, for example, these numbers decide which solution it is, but they never decide or, whether a unique solution exists or doesn't exist. So the uniqueness of the solution decides on this pure quadratic coefficient matrix. Well, now it may happen, and it will happen soon, that the whole procedure does not proceed up to the lower right corner. This is not really a problem. It's just a hint at the fact that we get a zero row, and then the whole procedure has to stop. This is not we cannot influence how far it goes. I just wanted to mention this so that you know. In the ideal case, it proceeds up to the lower right corner, but sometimes it ends early. So let's just start. You remember, if I use this as a tool, my aim is to eliminate everything in the first column except for the diagonal element, which I use as a tool. So what I do is I subtract the I subtract my working row by first scaling it with a factor of 2 and then subtracting it. This is my way of annotating. I told you you don't have to use this, but you may. So what I do is this. I take the number that's placed here, and then I go here and say minus 2 times the number here. So 2 minus 2 times 1 equals 0. That's my elimination. Then minus 2 times minus 3. In the end, it's minus 2 plus 6, and I get positive 4. 1 minus 2 times 5, so 1 minus 10 equals minus 9. And on the, of course, I go through the whole row, and then 12 minus 2 times 26. And this is, as you can surely calculate without a technical calculator. So this is 12 minus 52 and is exactly equal to minus 40. Okay, so far. Then in the third row, I add 3 times the first row so that I get 0 here. minus 3 plus 3 times 1 is of course 0. 5 plus 3 times minus 3 means 5 minus 9 equals minus 4, and minus 6 plus 3 times 5 minus 6 minus 15, no, sorry, minus 6 plus 15 then gets equal to 9. And finally, 2 plus 3 times 26, this is 2 plus 50, oh, sorry, 2, what is 3 times 26? Help me. Took too long. 78, of course, yeah. So 2 plus 78 is 80. That's it. And the first column has been fully eliminated. Now I proceed on the diagonal to the next element. There may be a problem which occurs always if this number is by chance or by accident equal to 0. In this case, I have firstly to exchange rows. So one good idea is to take a row from below and just pull it up, which is always allowed. And if even this doesn't help, you would have to change columns, to exchange columns, which is a little bit, well, you should avoid it if possible, because it means that you have to rename your variables, your unknowns. And that's not really so nice. You have to make a notation anyway. Okay, but this is not the case here, so we can just use the 4 as a tool to eliminate here and here. And now we have the case for the first time, I think, that these two numbers are of the sort that they don't have even a single common, so one is not a multiple of the other, let's say it in this way, so that it don't have even a single common divisor. The best and easiest way to solve this problem, and now to eliminate here, is to first scale the target row by the number that's encircled here, okay, and then add this number times the working row with the appropriate sign, and then to get 0 here. You understand what I mean? If I take this row times 4, and then I add 3 times this row, I get exactly 0 at this position, which is what I want. And you remember, this is even already a step which is according to the Gauss-Jordan elimination, which goes beyond what Gaussian elimination does. So we will always try to eliminate not only below the diagonal, but also above the diagonal. That's the point. So I do it, and I say 1 times 4 equals 4 plus 3 times 0. So I have to regard this because it's scaled to 4. This is my result. Then minus 3 times 4 equals minus 12 plus 3 times 4. Now this is fine because minus 12 plus 12 equals 0. My elimination was successful. Then 5 times 4 is 20 plus 3 times minus 9 means delivers 20 minus 27. So it results to negative 7 here. Then, now this is also something for number acrobats among you. 26 times 4, you get it. If you just double it twice, the double of 26 is 52, and then again times 2 results to 104 plus 3 times minus 40. So I have 104 minus 120. Oh, is that right? Yes, should be right. Minus, no, 104 minus 120, right? And okay, result is negative 16. Fine, so that's done. And then in the third row, I get, okay, I just have to add, that's nice, because the same number, plus minus. 0 plus 0 remains 0, of course. One of the advantages of this procedure is of course, that the zeros that you have once produced never go away anymore. And that's why it's so important to use this procedure strictly, you know, column by column and according to the order which I describe, not going around back and forth, because this might mean that some zeros get lost again. Okay, anyway, 0 plus 0 remains 0. -4 plus 4 equals 0. 9 plus -9, 0. Now you see, even here, already here, you can see that these two rows are quite obviously linearly dependent, which is okay. It depends on what what we want to have, but if we want to get a unique solution, this is really bad. Anyway, this is it's almost the same equation 2 times, and now the biggest problem would be if these two numbers are in contradiction to each other. And as you see now, 80 minus 40, if I add them, it results to 40. So here I have a 0 line with a contradiction. I can, just to make this clear, I can divide this row by 40, of course, this is always allowed, but in the end it means 0, 0, 0, 1, which is nothing else than the equation, the classical contradiction equation, or let's say the false proposition, which is called 0 equals 1. So this is interesting because you can, even if in your original system of linear equations, this kind of contradiction is somehow distributed around the numbers, you can always bring it to a certain point where it says, in the end, it says 0 equals 1. So this is the classical way of writing down a contradiction. It means that the whole system of linear equations is corrupt. It's not solvable because it's never possible to make all 3 equations true at the same time. So that means, but you've seen it here, if you just ignore the numbers on the right side, you would say, as soon as a 0 row appears, which means that structurally this system is underdetermined, as soon as this happens, it's possible that, depending on the number that I find here, that the whole system has not even a single solution. So this is closely connected to the case when a clean 0 row appears, where the system is multiply solvable in the end with an infinity of solutions. That's what I wanted to make clear. Okay, so this SLE in the end has no solution. That's fact so far. And in the other case, in the second case, I may just point here again. So I just take over these numbers. We do the same. We start out, well, I call them C and D now, just to not to mix them up with the previous example. So the same thing again. I mark this element. I try to eliminate here and here by subtracting 2 times the working row, 3 times the working row. I do it in a little quick mode now this time. So 2 minus 2 times 1 equals 0, as I wanted. Minus 2 times minus 1. Now take care, this means minus 2 plus 1. Sorry, minus 2 plus 2 equals 0. And right away, I mark this 0 in red color because this is a 0 I did not order. So this is what I did not want, but it may happen. Anyway, 1 minus 2 times 3 is 1 minus 6 is negative 5. And 1 minus 2 times 2, 1 minus 4 is minus 3. But even now, I have a problem because this is the element which I would need to use in the next step in order to further eliminate. Let's just delay this for a moment. In the third line, I get 3 minus 3 times 2, 3 minus 6. Oh, I'm sorry, I must go here. This is my working row. 3 minus 3 times 1 is 0, of course. Minus 3 times minus 1. Now this time, minus 3 plus 3 is 0 again. And minus 1 minus 3 times 3, so minus 9, minus 1, minus 9 is minus 10, that's okay, and 0 minus 3 times 2 equals 0 -6, so -6. So now you could say this is the worst case that can happen. Worst case for the following reason. If this element had been something, whatever, let's say 2, something not equal to 0, it would clearly have been the best idea to exchange these two rows. So to pull this row above this one and then to proceed with this element to eliminate. But in this special case, this is not possible because we have in the critical position, we have a 0 here and even here. And this row has been used already. So please don't start to pull a row below. Always, if you exchange rows, always take them from below. And if this does not help, the only alternative that remains is to exchange columns. So I always formulate this a little strictly in the sense that it's not so well. It's a little dangerous in the sense that you must not forget now to rename your variables, which are not, in this matrix notation, they are not visible. But it's important, if I exchange these two columns, it means that by the mathematical procedure, when I go on, it's as if the original x3 variable now immediately is called x2, and the x2 is now immediately called x3. I hope you know what I mean. So it's important that in the end, don't forget it, you must rename them. Okay, but we do this. And please don't exchange this column. It wouldn't help, firstly, but secondly, this has been done, so please leave it alone. Exchange these two columns, and so I get one by columns now 1 0 0, of course, then 3 minus 5 minus 10 here, and minus 1 0 0. This is now the third column, and still 2 minus 3 minus 6. Now we can proceed. We can mark this element and then say again, these two numbers don't have a common divisor, so I use the same trick as before. I take this row times 5, and then I add 3 times the working row. So 1 times 5 is 5, minus 0 is 5. This is the scaling of this element. Then 3 plus 3 times minus 5 means 3 minus 15 equals, oh, sorry, I think I've done it wrong again. 3 times 5 is 15, plus 3 times minus 5, of course, this is 0. That's what I want. Sorry. Then minus 1 times 5 is minus 5, plus 3 times 0, so minus 5 here. And then 2 times 5 is 10, equals 10, plus 3 times minus 3, so 10 minus 9 equals 1. This row is done as wanted. The second row stays as it is, and the third row now gets processed by taking by subtracting 2 times the working row, because this is the double number of this one. So anyway, I get, okay, 0 stays 0, that's no problem. Then minus 10 minus 2 times minus 5 gets 0. And also, this is by chance, I have zeros already here. No, it's not really by chance, it's because we eliminated before. But anyway, this stays a 0. And then last step, now this is important, minus 6 minus 2 times minus 3 means, or equals minus 6 plus 6, and this equals 0. Here, 0. So this time we get a clean 0 row, which is nice because in contrast to before, to the case before, this is without any contradiction, and it means that just simply one equation is missing, which is perhaps not so nice, but it's not tragic, because we then get a whole infinity of solutions. Now, what did I do here with my colors? This is about another important aspect, which I think Martin did not necessarily pronounce or enhance in the lecture, the so-called rank. I used this term last time also. The rank of such a system of linear equations is the following. After you performed the Gauss-Jordan elimination up to its end form, as far as it goes. Afterwards, you ask yourself, what is the size of the maximum size of a submatrix that has been diagonalized? So to diagonalize a matrix means to bring it in diagonal form, which in other words means that only on the diagonal the elements are different from 0. You see here, this is a 2 by 2 diagonal matrix. Also, the next step is usually to divide this line by 5, this one by -5, so that you even get the form of a unit matrix. You know what I mean. But the fact that this is a 2 by 2 matrix, in contrast to the 3 by 3 coefficient matrix, is a sign for that there are at least one or even more 0 rows. And in this case, or in any case, this gives you the so-called rank of the matrix. And this is an attribute of a matrix which is valid also then for the original matrix. So you see, if you look at this coefficient matrix, you would not immediately know that, perhaps you would, but perhaps not, you wouldn't immediately know that it will lead to a 0 row. So you would not be able to say what is the rank of this matrix. But in the end, even this matrix has a rank of 2, while the maximum rank of a matrix, if it's regular, we say it's regular if its determinant equals is unequal to 0, which also means that its inverse matrix exists. In this case, it has maximum rank of 3, but this one doesn't. This one is not invertible in the end, which is demonstrated by the fact that a 0 row appears. So this has rank 2, and it means if you compare the rank of the matrix to the dimension of your vector space, you find that 2 is lower than n equals 3. More clearly speaking, you find that the difference of these two numbers is the number of free parameters that you need for the general solution. So we have a clean 0 row, and now the end of this whole solution procedure is to find out how to formulate the general solution of this system of linear equations. And now I tell you how this works. Firstly, I'm quite sure at least one of you forgot to remember that we exchanged 2 columns, and so you would say this line, this row belongs to x3, and because x3 in this sense is missing its own equation, we could choose x3 freely. That's at least the method that I used last time when I said that the 4th row is missing, so x4 is just chosen arbitrarily by calling it lambda as a solution parameter. Well, that's the same thing here, but just some minutes ago, we exchanged these 2 columns, so we have to exchange x2 and x2 against x3 completely. It means that the former x3, whose equation is missing in quotation marks, is now x2. So the variable that should be chosen freely is not x3 anymore. It's called x2, and this is, I just put it equal to lambda freely. Okay, you know, lambda element r, real number. But then I go to the first line and fill this in. You see. Also, these scattered lines here around, scattered, I don't know, dotted line, whatever, around these 2 numbers has the following reason. It means because we got a 0 row here, we will not be able to eliminate anymore using this element because it's a 0. So we cannot eliminate in the 3rd column, and that's why these 2 numbers usually in this case are not equal to 0. This one is by chance, but generally speaking, as soon as the procedure ends in this form, you will notice that these numbers may not be eliminated anymore. So that's why I just I marked them with these dotted lines. So, but anyway, we can just extract the information of this line, of this var, which is 5 times x1 still, plus no times, so 0 times x2, sorry, x3, this is this corresponds to x3 by the exchange of columns, and then minus 5 times x2 equals 1. And since we just renamed x2 to be lambda, I can say 5x1 minus 5 lambda equals 1. And if I take this, I may put it here. If I say 5x1 minus 5x2, which is called lambda now, equals 1, I may put this in the form that x1 is isolated. Yeah. So I put this term to the right side, and then I divide everything by 5, and so easily I find x1 equals 1/5 plus lambda, depending on which value of lambda I chose here, but this is arbitrarily choosable from all real numbers. And then finally, the third and last unknown corresponds to the second row now, meanwhile, and it reads 0 times x1 minus 5 times x3, remember, by exchange, and then equals minus 3. So dividing by minus 5, I get x3 equals 3/5. So this is constant, although we chose lambda for one of the variables freely. So this can happen, and it happens exactly in the case when there is such a as I said, by chance or by accident, there is a 0 which we did not, well, which is just due to the structure of the original matrix. So anyway, now the question is, how can I assure you that this kind of solution with I should put this here with I put it here, lambda element r, which is our yes, our ground set, which we're using. How can I demonstrate that this is a line in a three-dimensional representation of this whole vector space? And this is quite easy if you remember your knowledge from school. In Germany, it's called Analytische Geometry. So analytic geometry, I don't know if this is the term in English, which concerns about the vectorial representation of lines and planes and things like that in mostly a three-dimensional geometrical space, and also then in an algebraic form. And from this, you know that you can put this whole solution into vector form, which I do now, but please take care. The order, of course, is x1, x2, x3. So if I take only the constants here, I have 1/5, 0, no constant, and 3/5 as the components of a starting vector, which already represents one of the solutions. Imagine you would choose lambda equals 0, so you would get x2 equals 0, x1 equals 1/5, x3 equals 3/5. This is this valid solution of the system of linear equations. Now, plus lambda times a certain constant vector, which just lists the factors for each of the unknowns before lambda, okay, or associated with lambda. So here the factor of lambda is 1 times lambda. Here, 1 times lambda. Here, no times lambda. So my vector is 1, 1, 0. If you read out this vectorial equation, line by line, row by row, you will find x1 equals 1/5 plus lambda, x2 equals lambda, and x3 equals 3/5. And that's what we got. So now this is the standard form. I can put it here. The standard form of a, let's say it's the so-called parameter form. Yeah, this is a this is a technical term, parameter form of a line in 3D. Okay, and so I can call it a solution line. By the way, in this case, it's a horizontal solution line even. This is quite a correct sketch of what we get. If you look at this, you can see, just a moment, you can see that since this, you know what this is? This is a starting point on the line, on the solution line, and this is a so-called direction vector along our line, while the lambda value is a so-called parameter. That's why it's called parameter form, a freely chosen parameter. But since the direction vector has a third component equal to 0, and usually the view is this one, that the first axis is pointing towards you, the second one to the right, the third one, you know, to the top. And so that means if you think about this vector, it has no up or down component, so it must be horizontal. But the whole thing is, well, rotated. If you just imagine you take the bird's view. From the bird's view, looking from above, you will see that this is a horizontal line, but which is well rotated. And so that's why it doesn't really look horizontal here, but this is a so-called perspective sketch. Yeah, I think you know what I mean. And here I have just a little location vector which points to our starting point with the coordinates 1/5, 0, 3/5. And because the middle component here is 0, this lies in the in the x1, x3 main plane, which is also called the second main plane of the whole coordinate system. Or how is it called? I say main plane in German. It's Hauptebene. Perhaps it's also called I don't know, fundamental plane. So in the side plane here. So that was a little more around explanation. So that's why it took some time. And after the break, it will get a little more complicated because we have a parameter even built into the system of equations beforehand. Ah, yes, I remember. My plan was to change colors here, but it doesn't really matter. So I would propose we make a break